So Bruce, you've been interested in applying game theory to the contest between pathogens and hosts, and you suggested in your talk earlier today that randomness might be a good strategy for our immune system.
Yeah, and it's a straw man argument. It's very hard to prove randomness, but when I think about it, when I think about complexity and I think about even game theory, if I want to create the most amount of responses I can and the most complexity with the least number of molecules, I would create a random system. And the reason I'm saying that we have to do that is because the perceived threats are infinite, and we can't predict when the next perceived threat occurs.
So where would you think randomness comes from in our immune system? At what stage? Or multiple stages, probably.
My guess is it comes in at multiple stages, and that as when we are very, very young, we probably have very stereotypical reactions.
Well, even before we're born, apparently there's something called the MHC system that is vastly variable between different individuals.
Well, that's how we define in transplant self from non-self, is through the MHC, or major histocompatibility antigens that are on chromosome 6. And that's
is that what they are for, or are they just there and they
well,
happen to get used to
actually,
that?
they're really to allow us to know self from non-self, particularly with intracellular invaders or pathogens.
So if you've got the right signals, you can say, I'm self, don't bother me.
Yeah, and they weren't made for transplant, but you can imagine if I see a protein in a cell, and I say that cell's self, that's me, and there's a protein I don't recognize in me, I want to get rid of that.
Right.
If it's a protein in a cell that's not me, why should I damage any one of my organs?
So there's enormous variation. It starts off in our genes and those sections to make lots of different antigens in our cells. But you were going on to talk about generation of randomness during development.
Right, but if you think about a system, and we can think of it in multiple ways, that we may have an antigen recognizing, a T cell recognizing an antigen in self, so it perceives a threat. But how it reacts to that, maybe for a virus in the beginning there's one response. But in a transplant, that antigen never goes away.
So if the system attacks a virus, it gets rid of it. But if it attacks a transplant, it's still sitting in there.
If the transplant's successful,
hopefully.
If the transplant's successful,
hopefully it's still there.
the antigen never goes away. So no matter what you do, it doesn't work.
So how can we tell the body, don't bother with this, it's okay, please leave it alone?
We've tried a number of ways. So in the past, we've tried to inject donor MHC antigens into the thymus, hoping for clonal deletion.
Does that work?
In animal models it worked. In humans it never did really pan out.
Oh.
We've tried to induce microchimerism, where
What's microchimerism?
where we have both self and non-self effector cells in our body.
So some antigen producing cells that are from us and some that are from somebody else.
Yeah, or effector cells as well. And that really, although people are continuing to study it, it hasn't led to yet to that key.
Mm-hmm.
So we're stuck with the fact that we have transplants that for the most part don't last forever, that eventually half of them are lost within 9 or 10 years.
So you talked before about how all of the research is about immediate rejection, but what really happens is people now get good control of rejection immediately, and then steadily there's loss over the next 10 or 15 years.
And that's one of the biggest insights we've learned over the last 20 years. The goal of every clinical trial up until about 10 years ago was, or up until 5 years ago, was acute rejection.
Stop it.
Stop acute rejection, everything will be fine.
Right.
What we found is we got acute rejection rates down from 60% down to less than 10%.
Uh-huh.
But we didn't change the so-called half-life or the average length that an organ lasts.
So that's surprising. I would think that because we can control early rejection better, you should have doubled how long the average kidney lasts.
And that's what the projection said. But when you actually looked at it, it was minimal difference.
What was wrong with our thinking?
We were thinking that it was only one response.
That was just the acute rejection
And
response.
there was one place in time. So there's a time dependency the longer we see that antigen, if we were to think about a war and we perceived a threat and we came at it with handguns,
Right.
and the handguns didn't do the trick, we might try tank. The tanks didn't do it, we wouldn't come back with tanks again. We would come back with something else.
So the immune system keeps seeing these antigens from a foreigner, and it attacks one. If that doesn't work, another way and another way.
Not that no one would ever ask me to be the master designer, but it would make sense, and it would make the most sense if we view it as a war, that would be the mechanism you would do. You wouldn't keep doing, a smart system wouldn't keep doing the same thing that didn't work.
So it seems to me the global interesting suggestion you're making is that natural selection has shaped a system that induces the immune system to a certain kind of randomness so that it can keep up with fast evolving viruses
Right.
and bacteria, even within the body.
Perceived threats, they're infinite, and they mutate by the hour.
Within us, right?
Within us, within hours.
But the
So
price
how
of
can we
that
keep
is,
up?
but the price of that is a system that's going to eventually get our transplanted kidneys, no matter what we do.
Right, and so at some point that response becomes maladaptive.
Right.
And I don't want to diminish the injury response. The tissue at some point may give up as well, that there's constant inflammation going on, and at some point the tissue decides, I'm no longer going to have the integrity, I'm going to stop differentiating, and I'll de-differentiate into scar.
Right.
So I think there's even more complexity when we think it's not only the effector arm of the inflammation,
Mm-hmm.
or the attack, or the injurious molecules, but how the organ reacts to the injury, or to the injurious
That's
insult.
fascinating.